the only true new operation that we have left for a computer to be able to perform is multiplication of numbers. So in standard multiplication, in base 10, 11 times 123, we could pretty easily evaluate that to be 1,353. But let's think about what 11 times 123 really means. I'm going to take 123 and put it out front, and I'm going to break up 11 into how many ones and tens it has. So 11 is essentially 10 plus 1. And so what this means is that I can effectively take 123 times 10 by the distributive property plus 123 times 1. Now when we do multiplication the old-fashioned way, by hand, this is normally how we would set up this first multiplication. And the second multiplication would be 123 times 1. Now we have to add these together. So in this case, 0 times all of these values just produces zeros across the board. But now that we're working with tens, we need a shift. We need a shift value, which basically means that now we're working in the tens place. Sometimes we just leave this blank and kind of shift one value over here. But now I have 3 tens here. I have 1 times 2, that's equal to 2. And then I have 1 times 1, which is equal to 1. And so what I essentially have is I have 123 tens. And that amounts to 1,230, which now I can add those two values. And similarly here I just have 123 times 1. I have an extra value there. So I have 3, 1 times 2, 1 times 1, and so that comes out to 123. And now all that's left is to take 1,230 and add that to 123, which gives me the same number that we came up with up here, 1,353. When we work in binary, we kind of work exactly the same way. So if I were to represent this in binary, my first step would be to convert these. And doing so would yield 1011 is the base 2 representation of 11, 111, 1011 as the binary representation of 123. Now one way I can again do this is to break this value up into how many 2 to the zeros it has, how many 2 to the firsts it has, how many 2 squareds it has, and how many 2 to the thirds it has. And I could kind of break that up in this same fashion. So one way to approach this would be to take 1111011 and multiply it by how many 2 to the zeros there are here. And then repeat the same thing, but multiply this by 10 to indicate that there's 1 2 to the first. But we can do this in terms of standard multiplication. And we can do it exactly the same way. So let me place these values here. Okay, so when I multiply, I'm going to do the multiplication across, which is always going to result in ones or zeros. So 1 times 1 is 1, 1 times 1 is 1, 1 times 0, 1 times 1, 1 times 1, 1 times 1, 1 times 1. So this is identical to basically what we did right here, where we just said we took the first digit, or the first value, and multiplied it by how many ones the second value had. And next, what we had to do is figure out how many tens it had, and it had one 10. So in this case, we're not figuring out how many tens it has, but how many 2 to the firsts it has. Well, it has 1 2 to the first. So that means that I need a shift bit to now get me into 2 to the ones. And again, I can repeat. 1 times 1 is 1, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1. And now, because I'm moving on to the third column, now that would be like saying 123 times 111, we would also need a 123 times 100 below it. So that's going to give us 2 shift bits. And again, we could kind of omit these if we wanted to. And now we begin our multiplication with the number of 2 to the seconds that we have. So this is going to be 0 all the way across the board. 0, 0, 0, 0, and then 3 more. Next we move on to the number of 2 to the thirds it has, and that's like the same thing as saying how many 1,000s in decimal representation. So now my shift bit has to be across for the first 3 elements. And now I can repeat. So essentially I'll have 1, 1, 0, and then followed by 4 ones. And now what this boils down to is the sum of these 3 numbers. Essentially what we figured out here is how many 2 to the zeros we have, how many 2 to the firsts we have, how many 2 to the seconds we have, and how many 2 to the thirds we have. So now addition takes place in the same way we dealt with binary addition in the last video. So 1 plus a bunch of zeros is 1, no carry. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 1 plus 1 is 1, 1, plus another 1. Well, what's that going to give us? Well, if we take 1 plus 1, we know that we get the binary representation of 2, which is 1, 0. Now, if we add 1 plus 1 again, we get, again, 1, 0. And now we want to add those 4 numbers together, so that's the same thing as adding 1, 0 plus 1, 0, and that gives me 0. This gives me 0 with a carry of 1, and so this is equivalent to saying this is equal to 4 right here in base 10. Now, if you don't like this, if you don't like the number of carries that have to take place, one other way to do this is to add these values in pairs first, and just do 2 at a time, then add the third one, then add the fourth one. So, or better yet, yeah. So if we add these 2 together first, come up with that result, and then add this row to it, come up with that result, and then add this row to it, we could also get away doing it that way. So how do we carry a 1, 0, 0? Well, this digit is a 0. We have a carry of 1, 0. So one way to do that is to carry the 1, 0 here. But then we're going to have to worry about carrying this 1 to this other column. So to save ourselves that extra hassle, we could just carry a 0 here and carry the 1 over to this column. And so now we have 1 plus 1 is 1, 0. Carry the 1. And now we have 1 plus 1 plus 1 plus 1, which is 1, 0, 0. And then we have one more 1, which is 1, 0, 1. So we'll carry a 0, 1, or a 1, 0. So we'll carry a 0 to this column, we'll carry a 1 to this column. This will give me 1 plus 1 is 1, 0. 1 plus 1 plus 1 will give me 1, 1. And now I have 1 plus 1, which will give me 1, 0. So to check that we get the same answer, we know that this is 2 to the 0 plus 2 to the first, 2 to the second, 2 to the third, plus 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth, 2 to the ninth, 2 to the 10th. So if we verify this and get these exponentiated, we get, lo and behold, 1,350 as expected. So if you don't like adding 4 binary numbers together at the same time and having to deal with all these extra carries, the other way to do it would just be to add what I'm calling rows 1 and 2 together first. So we have 4 binary values to add together, and we can add them in pairs. So I'll just go ahead and do it here if you're interested in seeing how this pans out. If we add these together, we get 1. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. Carry the 1, and 1 plus 1 plus 1 is 1, 1. 1 plus 1 plus 1 is 1, 1. 1 plus 1 plus 1 is 1, 1. 1 plus 1 is 1, 0. Now we can take this number and add to that this next row, which is this one here. So let's go ahead and carry that out. Well, that's just going to be the same number because we're adding just a whole row of zeros. So we'll get 1, 0, 0, 0, 1, 1, 1, 0, 1. And that's now us taking the result here and adding row 3. Finally, we could take that value and add row 4 to it. So I'll go ahead and place that right over here. You can tell it's getting kind of messy. And we'll take that, we'll paste it here. And so now we can conduct our final addition. This is involving row 4 added to our result here. And hopefully we should get the same result. So let's see, 1 plus 0, 0 plus 0, 0 plus 0, 0 plus 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 plus 1 is 1, carry the 1. And 1 plus 1 is 1, 0. And you see that we get exactly the same result, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1. And those two answers match up. So you can do this however you want. With a computer algorithm, we'd have much more efficient means by which to do this, but perhaps we would also instruct the computer to say, okay, if there are multiple rows of multiplication, given the fact that one of our binary numbers requires 4 rows of multiplication, then we could simply have the computer check the length of this binary digit, or this bit string, and then say, okay, that's that many minus 1 additions will need to take place. So row 1 plus row 2, row 2, the sum of that plus row 3, the sum of that plus row 4. And we could have this split up into multiple steps. So that's essentially how binary multiplication works. It's a very important thing to understand how computers deal and process with numbers. Now subtraction gets interesting, but and division gets a little bit more interesting. However, multiplication and addition are really the only two properties that we need. We can do the rest with just addition and multiplication, though we're not going to go into that here.